Alright everybody, welcome back. In this video we're going to talk about information from section 10.13 of AP Calculus BC, radius and interval of convergence of power series. Okay, so basically this lesson we're going to find two very important, related but slightly different characteristics of what are known as power series. We're going to find the radius of convergence of the series, and we're going to find the interval of convergence of the series. And we've mentioned this term before, but not this one. So we've mentioned this a long time ago when we were talking about geometric series, but we're going to expand on the idea now. First off, we need to know what a power series is. A power series is an infinite series where the terms contain coefficients and powers of a variable. Usually we use x, sometimes t. For instance, the most common examples of power series are related to the Taylor and Maclaurin polynomials that we talked about in our last lesson. So if we take those polynomials and instead of stopping after 4 terms or 5 terms, we let that continue and continue to build terms onto that polynomial forever and ever, we've built a power series. Okay, and so you see that right here in our box. Power series is something, here's the Maclaurin form of a power series, here's the Taylor form of a power series, the sum from 0 to infinity of a sub n x to the n. There you see what that looks like. That's a power series. It continues on indefinitely past that nth term. Same thing here. We build it exactly how we build the polynomial, except we continue on beyond the nth term and go on forever and ever. The domain of any power series is the set of all x values for which that power series converges. That is going to be our interval of convergence. So for instance, when we were talking about a geometric series before, the interval of convergence were the r values that caused that series to converge. When we talk about other power series, there will be some interval, some set of x values, on which the power series converges, and that's going to be the domain of our series, because that is the value of all the x values, where the series is the exact same as the function. All right, the convergence theorem for power series. When we talk about a power series, the sum from n equals 0 to infinity of c sub n x minus times the quantity x minus a to the n with respect to convergence, there are 3 possibilities. Possibility number 1, there's some positive number r, so that the series diverges whenever the absolute value of x minus a is greater than r, but converges on the interval where the absolute value of x minus a is less than r. Okay? The series may or may not converge at the endpoints, and we'll talk about that more later. Second possibility, the series converges for every x, all real numbers, in which case the radius of convergence, r here, this capital R, is equal to infinity. I blew the surprise. And the third possibility is that the series just converges at the center and diverges everywhere else. And in that case, the capital R is equal to 0. And so we've got 3 possibilities. R is 0, R is infinite, and in this case, R is between 0 and infinity. Okay? This number R is what we call the radius of convergence. Kind of like the radius of a circle, the radius of convergence gives you half of the interval of convergence, just like the radius of a circle gives you half of the diameter of the circle. And the set of the values of x for which the series converges is the interval of convergence. Our primary tool for helping us to find the interval of convergence of any power series is going to be the ratio test. So let's go ahead and we'll start looking at how this works. We'll look at the ratio test for interval of convergence. We'll give you some last thoughts on the narrative here, and then we're going to bust into some examples. So, if I'm using the ratio test to find the interval of convergence, I go ahead and I set up the ratio test for a power series sum from 1 to infinity of a sub n. I'm going to find this limit as n approaches infinity of the absolute value of a sub n plus 1 over a sub n. If this value is less than 1, then the series converges on a finite interval. That's the first of those 3 style convergences that we were talking about in our convergence theorem on the previous page. If this limit is equal to 0, that tells you that the series converges for all real values of x. And if the limit is infinite, that tells you that the series converges only at the center, single point. All right, so these three connect to our convergence theorem. Let's go back here for a second. Connect to our convergence theorem. Line 1 of this matches up with line 1, line 2 matches up with line 2, line 3 matches up with line 3 on our ratio test to find the interval of convergence. All right. Final thoughts before we get to this. All right. When we have a series that converges on a finite interval, we're going to need to test the endpoints of that interval to determine if the series converges there or not. So anytime we end up with case 1, we're going to have to look at what happens at the endpoints. All right. And how we do this will depend on what the series looks like, and you'll see that as we do more and more examples. A second thing, a series converges absolutely in the interior of its interval of convergence. All right, so say the interval of convergence is from, -2 to 4. For every x value that's not -2 and not 4, that's in between these two values, this series converges absolutely. At the endpoints, it's possible for the series to either converge absolutely, converge conditionally, or diverge, and we should be familiar with all of those terms by now. All right, that's all the info. Let's get down to business and start looking at some examples. Example number 1, we are going to find the interval of convergence, the radius of convergence, where the series converges absolutely, and where the series converges conditionally for this series. The sum from 0 to infinity of -1 to the n times the quantity 4x plus 1 to the n. So we're going to go ahead and set up our ratio test. Take the limit as n approaches infinity of a sub n plus 1 times a sub n, divided by a sub n. And if we take this limit, well, even before we take this limit, this is the limit as n goes to infinity of the absolute value of -1 times the quantity 4x plus 1. The limit of that as n goes to infinity is just what's inside of there. In order for this to converge, since this is a variable expression, it's not equal to 0, it's not infinite. There are going to be values of x that make this less than 1, and other values of x that do not. All right? It didn't come out to 0, and it didn't come out to infinity when we ran our ratio test. So we've got the finite interval of convergence in this particular example. So we're going to go ahead and set that so that this is less than 1. And now we can go ahead and solve this inequality to find my interval of convergence. We'll go ahead and add 1 to all three parts and divide all three parts by -4. And this gives us our base interval of convergence. -1/2 is less than x is less than 0. Now we need to consider what happens at the endpoints in this. So we're going to start by looking at the first endpoint at x equals, do I want to do the right endpoint or the left endpoint? Let's do the left endpoint first. At x equals -1/2. I'm going to go ahead and put -1/2 into our series here in place of x. So this is going to be -1 to the n times 4 times -1/2 plus 1 to the n. And if I simplify this, this gives me sum from 0 to infinity of -1 to the n times -1 to the n, which is just the sum from 0 to infinity of 1. This diverges by the nth term test. So this endpoint is not included in our interval. So we're not going to include that. We're going to look at the other endpoint at x equals 0. I substitute 0 into this infinite series, and that gives us -1 to the n times 1 to the n. This also diverges by the nth term test. So we're not going to include either of these endpoints. All right, So let's start answering our questions. The interval of convergence is exactly what we found here. We tested the endpoints. We didn't need to include either endpoint. The radius of convergence. The radius of convergence is half of the length of this interval. This interval is 1/2 units wide. So the radius of convergence here is 1/4. Where does the series converge absolutely? It converges absolutely everywhere in the interior of this interval. The only places that it could potentially converge conditionally would be at one of the endpoints, but we found that it diverges at both of the endpoints, and therefore the places where this series converges conditionally, there are none. All right, let's see. Let's do one more here. Let's jump on example 2. Find the interval of convergence, the radius of convergence, where the series converges absolutely, where it converges conditionally. I set up my ratio test. Limit as n goes to infinity of x plus 5 to the n plus 1 over x plus 5 to the n. Again, this turns into just the absolute value of x plus 5. This is not infinity or 0, so we're going to see where this is less than 1. We set up our inequality. We subtract 5 from each part. And we get that our interval is from -6 to -4. We test at x equals -6. This is the sum from 0 to infinity of -1 to the n. That diverges by the nth term test. At x equals -4, this is the sum from 0 to infinity of 1 to the n, which also diverges by the nth term test. So again, we're going to exclude our endpoints, and this right here is our interval of convergence. So there we go, the interval is from -6 to -4. The radius of convergence is half the length of the interval. The interval is 2 units long, so the radius of convergence is 1. It converges absolutely everywhere in the interior. And again, it could converge absolutely at one of the endpoints, but it doesn't converge at either of the endpoints here. And therefore, there's nowhere where this converges conditionally either. All right, that takes us to the end of example 2. All right, we're going to call it quits for this video there. We're going to come back and do a bunch more examples on finding interval of convergence, radius of convergence, etc. In our next video, our second video on this lesson. So come on back and join us next time when we do the second half of section 10.13. Have a great rest of your day, everybody, and bye-bye for now.